In this video, we introduce and discuss the concept of a Venn diagram as it applies to the joining of two tables using SQL. And we also discuss how null values in a foreign key can be modeled with a special kind of Venn diagram. Here are the Venn diagrams we will use in our illustrations. The first Venn diagram is our special model. It illustrates what happens when a foreign key value is null. We will look at the data in a moment to see the null values. The next three Venn diagrams illustrate three common types of joins that we write in SQL. A left outer join, which is all the records from one of the two tables being joined. An inner join, which is the intersection of two tables being joined, and a full outer join, which is all the records from all the tables being joined. You're welcome to follow along with this slideshow. Look on Blackboard under Course Documents for credentials to the Joins and Null Key Values database. Open SSMS, log in, and you will find the tables that we are discussing. This is our basis. We have a story, which is an English language description of what our schema is modeling. The story says that we have fish and we have baits. We keep those on file. Each fish that's on file may have a favorite bait or may have no favorite bait. That is one or none. Some baits that are on file are not preferred by any fish. This works out to be two tables, a table called bait, or T-bait if you prefer, and a table called fish. I've provided here the structure of those two tables. You can see that they each have a primary key, which is an integer, and they have a text value, a string value describing what is in the row. The bait table has a column called bait. The fish table has a column called fish. Also in the fish table is a foreign key called bait ID that relates to or connects to a row in the bait table. We have a foreign key primary key relationship. The primary key is in the bait table called bait ID. The foreign key is in the fish table, also called bait ID. Whenever possible, I strongly prefer to name my foreign keys the same name as the primary key to which it is relating. It just makes semantics a lot easier. This is discussed in the naming conventions document that I posted on Blackboard in your class. We've seen the schema. We've heard the story. Let's look at the data. Each table is very small. These are for illustrative purposes only. You should not take these with you when you go fishing. In the fish table, we have 7 records. The fish ID, the fish, and the bait are all populated, except in row 4 and row 7, there is no bait ID. It's not 0, it's not blank, it's literally null, meaning there is nothing in that field. That means semantically that that particular fish in row 4, the walleye, does not have a bait. This is a design decision that I made. I decided that there may be fish that do not have a bait. I get to decide that because I designed the schema. I am the domain expert. In the real world, this may not make any sense. You may be providing a database for a customer wherein all the fish must have a bait. In other words, null values in the foreign key are not permitted. We can certainly set our tables up that way, but we're doing it with null values in the foreign key to illustrate the kinds of joins that happen when there are null values. So we're doing this on purpose. Over in the bait table, there are 8 records. And I alphabetized them here, but there are primary keys 1 through 8. I can tell you that not all the baits have a corresponding fish. The reason I know that is because I'm looking at the data. And I, for example, pick cricket. The cricket row in the bait table is primary key 1, bait ID 1. If I look over here in the foreign key table in the fish table, there is no bait ID 1. Therefore, I can tell by looking at the data that not all the baits have a corresponding fish. And again, that is by design. We did that on purpose to illustrate what happens when we join these two tables together in this special condition. In the next slide, we introduce the concept of the inner join. We're relating the two tables by their common field. The common field is bait ID. Each table has a column called bait ID. In the bait table, bait ID is the primary key. In the fish table, bait ID is the foreign key. The query that we write, select star from bait, inner join fish on bait ID equals bait ID, order by fish ascending. In the upshot, the result of that join, the result of that select statement is the intersection or the gray area in this Venn diagram. We can graphically illustrate then what we expect to get out of this select statement by drawing the Venn diagram. When you see the two overlapping circles with the gray area in the middle, the common area between the two circles, that is an inner join. Over on the right of the slide, there is the result of that select statement. We only get the records that are common to both tables. We only get the records where both tables have a common value in the bait ID. And that answers the question at the top of the slide. What are all the fish that have bait? Since we did a select star, we got all the columns in both tables. We could certainly trim that down if we just wanted the fish and their baits, because the bait ID values and the fish ID values don't have any meaning to the end user. We typically leave those out. But for this illustration, I wanted you to see all the columns in all the rows. In the next slide, we illustrate an outer join. Our Venn diagram is gray, where we are getting all the records from a particular table. So we're getting the intersection of the two tables plus all the records in the left-hand table, regardless of whether there was a corresponding value or not in the foreign key primary key relationship. Now, a left outer join simply means that the first table in the join is the left-hand table and the second table is the right-hand table. So in this case, we're asking for a left outer join where fish is the left-hand table and bait is the right-hand table. We could easily swap those and then it would become a right outer join, but this is how we read the SQL. The first table that appears in the select statement is the left-hand table. The second table that appears is the right-hand table. Referring to the diagram then, fish is the left-hand circle and bait is the right-hand circle. When we execute this SQL statement, we get these results. Notice, please, that in the second row of the results, there are a lot of nulls. That means that the bluegill fish doesn't have a bait ID, which is that first null under bait ID. And since there is no bait ID in that row, there cannot be a corresponding row in the bait table. Therefore, the two columns from the bait table are also null. In the next slide, we're doing our little trick with the Venn diagram, and instead of the common area between the two circles, we're looking at part of one circle that does not intersect with the other circle. And the question we're answering is, what are the fish that don't have bait? In other words, what fish have a null value in the foreign key field? What fish rows do not relate, do not connect to the bait table? And here's the trick. We're saying only give us rows where there was no bait, where the bait is null. It still does the join, but it filters out every other record except for the records that are null. The result of that is only 2 rows, the bluegill and the walleye, because they had a foreign key value of null. And that can be drawn this way. That shows us that there is no corresponding record in the bait table for those 2 records in the fish table. And that's not a common use of the Venn diagram, but it does illustrate this type of outer join. On the final slide, we're doing a full outer join, which is everything from every table. We're going to get a row in the query for all the fish, a row in the query for all the bait, and you can see that the results have lots of nulls in them because there were some fish that didn't have baits and there were some baits that had no corresponding fish. So we get a lot more than just a few rows in this result set. The syntax here is to use the word full when you define the outer join. That tells SQL Server you want everything in both tables, even if there was no connection between those 2 rows. This is something we do once in a while. We'd have to be careful with the report that we generated because there would be a lot of blank values in here and we'd have to explain it carefully. But sometimes we do want to know what is in both tables, and we want things that don't relate between the 2 tables to show up in the report. On the last slide, I provided a few resources that you can look at. There are numerous places you can go online to read about Venn diagrams mathematically, how they work in set notation, how they work in algebra, or you can look at how they apply to databases, because this is a common way of illustrating how tables are joined by drawing Venn diagrams to illustrate inner joins, outer joins, full outer joins, and the join that I introduced, which is the outer join without the nulls. At this point then, I would encourage you to grab a join. I am on slide 6. You can copy this text. You can go to SQL, you can go to SSMS, and if you're logged in correctly with the correct credentials, you can access the database called joins and null key values. You can open up a query window. You can paste in the SQL right off the slide, and you can execute that. And you get the same results that we got on the slide. We only get the rows that are common to both tables. In other words, we're only going to get rows where the foreign key in the fish table is non-null, and there is a corresponding primary key in the bait table. I encourage you to read more about Venn diagrams and how they apply to database joins, and I expect you to be able to understand, apply, and explain inner joins, left and right outer joins, and full outer joins. And once you've understood those, make sure that you can grasp the concept of applying a where clause to exclude certain records based on whether foreign keys are null or not. And part of our job as database designers, developers, administrators, programmers is that we can start with a natural language question and map that into a SQL query to give us the desired results. Remember that a natural language question will very often be unclear. This is English. It's casually spoken. We understand it in general when we talk to each other, but there is often a lot of assumptions that are made, and there is often a lot of questions that have to be asked. So don't be shy. If you're given a natural language question and your job is to convert that to a query, to provide information to the customer, be sure to ask for clarification if necessary. There's nothing wrong with asking for clarification. You're expected to do that in order to provide the most accurate and useful results for the end user. Thank you.